as the emeritus professor, retired professor associated with CSEi, to introduce one of the most early career speakers we've had in this seminar series, which is Erin, Emme, who comes to us from the University of Illinois at Champaign, Urbana. Now, she's been there for something like 6 or 7 years.
9.
Because she has received her Bachelor of Science, her undergraduate degree there, and is going to receive her PhD. She's already scheduled her defense for February next month. And she's been in environmental engineering the entire span of her career at the University of Illinois. And her mentor there is Professor Hannah Horowitz, which, if you're with the Department of Geophysical Sciences, she, I think, was a classmate of Sonny Park, our seismologist, so there's a little bit of connection there at Harvard University. Erin has an incredible list of notable awards and honors. She has been an NSF NCAR Graduate Advanced Study Visitor, working with Jack Chen at NCAR. And many of you may have heard of NCAR recently. I hope that continues to work out well. And she's won more than one Outstanding Student Presenter Award at the various AGUs over the recent past. She has 2 very important publications that have come out in 2025. The first, at Geophysical Research Letters, was Impact of Seasonality on Climate Outcomes for Mid-Latitude Marine Cloud Brightening. And I learned from reading this paper that you can shift El Nino and La Nina depending on how you do marine cloud brightening. Can you imagine a world where we didn't have El Ninos? Some people would think that's good, some people would think the world is too boring without an El Nino. And then she also published in Atmospheric Chemistry and Physics, Atmospheric Chemistry and Physics, also in 2025, Impacts of Sea Ice Leads on Sea Salt Aerosols and Atmospheric Chemistry in the Arctic. So this was a basic science research that looks at how in the wintertime, even in the wintertime when the sea ice breaks, little bits of ocean is exposed, and this puts aerosols into the atmosphere. And she's working on a paper right now for JGR on the topic of today's talk. After she defends her thesis in February, she's going to move to University of Colorado at Boulder to work with the distinguished sea ice scientist Marika Holland on cloud brightening and sea ice. And this is a new project funded by the Grantham Foundation. And I'm going to only say one personal thing about Erin, and that is that she was the captain of the University of Illinois Collegiate Diving team. And I told her this morning that I had been up on top of a high dive, a high platform once, but I've climbed the ladder twice, which means I had to climb back down. So I'm going to give it over to Erin to speak on deployment strategy shapes the polar climate response to marine cloud brightening.
Thank you so much for having me here today. I'm really excited to be sharing some of my recent work with you. As Doug mentioned, the title is Deployment Strategy Shapes the Polar Climate Response to Marine Cloud Brightening. If anyone's interested, I recently submitted this for publishing with JGR Atmospheres. So the preprint link is up in this top left corner, but I'll show it again at the end of the presentation as well. I'd just like to quickly thank my co-authors, Jack Chen and Hannah Horowitz. But with that, I'll get started. So I wanted to start this talk off by briefly giving a background on how climate change is impacting the polar regions. Sea ice levels in both the Arctic and Antarctic are currently reaching near record low levels. The figures here show the observed seasonality of sea ice area for the Arctic on the left and the Antarctic on the right. 2025 sea ice area, which is shown in this red color here, is notably lower than years past in the Arctic. And in the Antarctic, trends are a bit less clear over this recorded historical time period, but we do see recent years like 2025 as well as 2023 shown in this light gray color are also lower than years past. But I'll touch on this again in a few minutes. Earth system models such as the Community Earth System Model version 2 or CESM2 have been used to project future levels of sea ice. It is important to note, though, that sea ice predictions with Earth system models is highly uncertain, but we are able to paint a picture of what's going on in the poles with these models. So the figure here is from a study which shows different configurations in projecting future sea ice conditions within the Arctic. The top here is for September, which is when sea ice reaches a minimum in the Arctic, and the bottom is the March sea ice area when sea ice reaches a maximum. And the red lines here also represent observations, so we see that CESM2 is doing a pretty okay job here in predicting those sea ice projections. And we see here notably that September sea ice is much more impacted than the March sea ice. We get this decreasing trend in sea ice over the recorded time period, and also a projection of a mid-century ice-free Arctic in September. In fact, this study shows that warming must stay below 1.5 degrees C warming above pre-industrial levels in order to avoid a future ice-free Arctic summer, which none of the CMIP6 scenarios achieve. Oops, I'm sorry. Also, the March sea ice area is impacted by climate change. We do get this decreasing trend toward the end of the century, but definitely not to the extent of September. According to the latest IPCC report, there is low confidence in model projections of Antarctic sea ice. However, recent trends point to a declining state. The figures here show the Antarctic monthly sea ice extent anomalies in the million kilometers squared on the top and the percentage anomaly shown below. These are observations, not model projections here. And over this recorded historical time period, which is shown in gray, we don't see a clear trend in the Antarctic sea ice. There are natural fluctuations, of course. But in the early 2000s, shown in this blue color here, sorry, it's a little low for me to move my mouse, where there is an increase in Antarctic sea ice, but this is followed by a rapid decrease occurring in 2016, and these low extent sea ice anomalies have continued to the present day. The study here links these low sea ice anomalies to subsurface ocean warming in the Southern Ocean. And this Southern Ocean warming has been attributed primarily to increasing greenhouse gas concentrations, with ozone depletion playing a secondary role. So there is an anthropogenic element here. And if you refer to the very bottom figure here, the shift from cold subsurface temperatures shown in that blue color to warm subsurface temperatures shown in that orangey red color occurs approximately 1 year before the change point from positive to negative sea ice anomalies, strongly suggesting that this low sea ice extent state is due at least partly to subsurface ocean warming. And when talking about these changes in polar sea ice, it's important to mention that polar sea ice is a critical component of the Earth system, with climate change triggering a range of impacts. These impacts will affect ecosystems, indigenous populations which rely on the sea ice for their livelihoods, as well as important Earth system processes, such as the surface energy budget, hydrological cycle and ocean circulation, and also climate feedback, such as the albedo feedback. A proposed method to help mitigate the impacts of climate change, such as sea ice loss, is marine cloud brightening, or MCB. And some of you may already be familiar with MCB, but I'll just briefly go over the concept here. Marine cloud brightening is a solar climate intervention strategy, and the idea is to inject sea salt aerosols into the marine atmosphere. Sea salt aerosols are highly hygroscopic, meaning that they readily take up water, so they act efficiently as cloud condensation nuclei, increasing the cloud drop number concentration and decreasing the mean droplet size of clouds. Overall, this leads to an increase in cloud albedo, lifetime, and the aerial extent of clouds. All of this to say, marine cloud brightening creates a cooling effect. A real-world analog of MCB are the ship tracks that occur in shipping corridors due to the exhaust of ships seeding clouds with emissions of sulfur and other aerosols. So you can see an example of ship tracks here with these lines representing those ship tracks. Ship tracks have been known to induce quite a bit of cooling on a global scale. up to minus 0.06 to minus 0.6 watts per meter squared, or 10 to 40% of the total aerosol cooling effect. However, in recent years, there have been regulations put onto shipping fuels, which has likely reduced this cooling effect since 2020. Model simulations have shown that the large-scale deployment of MCB can lead to a significant amount of global cooling, even enough to potentially apply MCB to restore polar sea ice. The figures here are from 2 studies which have explored this application. The left figure here is from Latham et al. 2014, where they simulate MCB over 3 regions, largely in the tropics and subtropics due to the presence of stratocumulus decks. And they find that by applying MCB within these regions, they are able to enhance the sea ice edge. So we see the green line here represents MCB, and the red represents climate change, where you see an enhancement of that sea ice edge. The right plot here is from Rasch et al. 2009, where they simulate MCB over really large portions of the ocean, 40% and 70%. And they found that by applying MCB in these regions, they are able to restore sea ice relative to their climate change scenario. So we see in the top panel here, which is their climate change scenario, a decrease in sea ice at both poles. But by applying MCB, we get increases in sea ice fraction, which is shown in the red color in those bottom 2 panels. While these 2 studies have shown the potential for MCB in restoring polar sea ice, these MCB strategies are also shown to trigger negative climate outcomes. The figure here shows the surface temperature change pattern for the climate change scenario in this top figure here, and the 70% seeding strategy from Rasch et al. 2009, where we see that the cooling pattern from MCB is quite non-uniform. You get warming in regions where that may not have occurred otherwise from climate change, and of course we do get a significant amount of global cooling here, but the cooling pattern, like I said, is non-uniform and also resembles a La Niña state with this negative temperature anomaly within the Eastern Pacific. This strategy has also been shown to shift tropical precipitation patterns, or the intertropical convergence zone, which we can see in the changes in precipitation along the equator here. So overall, these negative climate outcomes suggest that these climate intervention strategies may not be viable. So there is a need to understand how more up-to-date and potentially more successful MCB deployment strategies impact the polar regions. So for this study, we analyzed 9 recent MCB simulations performed with the Community Earth System Model version 2, or CESM2. This is a fully coupled Earth system model with model components simulating atmosphere, sea ice, ocean, land ice, as well as other processes like river runoff, ecosystems, and waves. So it's a really detailed model which has different model components simulating important Earth system processes, all coupled together. And for our MCB experiments, the model configuration is identical, but each experiment varies in the timing and location of MCB deployment. So each of our MCB experiments branch off of the control in 2035, which is when MCB is applied to the model. And most of our experiments here are run for 35 years, meaning that MCB is applied for 35 years, with the exception of a few experiments which I'll mention shortly. MCB is simulated in the model by artificially increasing the cloud drop number concentration of low clouds within the boundary layer to 375 per centimeter cubed. So this is a way of artificially brightening the clouds in the model without directly injecting the sea salt aerosols in order to bypass aerosol cloud interaction uncertainties. These experiments target the global temperature restoration of 1.5 degrees C warming above pre-industrial levels. So they do not explicitly target sea ice restoration, but they do impact the polar regions nonetheless. As I mentioned, this is a fully coupled model. The control experiment is the spun-up first member of a 16-member ensemble of simulations performed from 2015 to 2100, following the moderate future warming scenario SSP2 4.5. This is one of the shared socioeconomic pathways outlined in the IPCC report and is a common scenario chosen for geoengineering model simulations. The first two experiments that I introduce here, the Chen 20% and Chen 5% ensemble, base the MCB deployment locations on the susceptibility to cloud seeding. Physical factors which affect the susceptibility of a region include the amount of incoming solar radiation and low clouds present. Chen et al. 2024 performed calculations ranking the susceptibility of each model grid box over the ocean. So the most susceptible regions have the most incoming solar radiation and low clouds present, meaning that there would be a large negative shortwave cloud forcing response to MCB within these regions. The Chen 5% ensemble is an example of this. We use the first 5 members of the 10-member ensemble experiment, and it deploys MCB over the top 5% of the ocean surface most susceptible to cloud seeding. And this is shown within the deployment maps here in red, where the Chen 5% scheme largely deploys MCB over the tropics and subtropics. The Chen 20% scheme deploys MCB over 20% of the ocean surface least susceptible to cloud seeding. So this is largely within the mid-latitude regions shown in blue within the maps here. Chen et al. 2024 show that the least susceptible MCB approach results in more favorable climate outcomes than the most susceptible approach. And the most susceptible approach is kind of the historical regions that we've really focused on for MCB. So this was a shift in, the thought of where we should be deploying MCB.
Can I ask a question? Is the difference between least susceptible and most susceptible, is that a geographic position in the ocean that differentiates the two, and it indicates where you're actually affecting the clouds?
Yeah, so the locations vary because susceptibility is variable in both time and space. So it depends on the climatology of the regions. The physical factors, I guess, affecting that would be the amount of incoming solar radiation and clouds present. So you'd imagine towards the tropics and subtropics, which are near the equator, you'd get more solar radiation coming into those regions, which is why the Chen 5% ensemble here focuses the deployment within those regions. But I didn't mention, susceptibility is variable in both time and space, so that's why we see different deployments within each month for these two schemes here. So here I'm showing the surface temperature change plot for the 5% scheme circled on top here, and the Chen 20% scheme on the bottom here. The Chen 5% scheme results in a significant amount of global cooling, but the cooling pattern is non-uniform. We see again that negative temperature anomaly in the eastern Pacific, which suggests conditions are in a La Nina state. And for the Chen 20% scheme, we get a much more uniform cooling pattern while also hitting the target of 1.5 degrees C warming above pre-industrial levels. And we confirm with the Niño 3.4 index that the Chen 5% scheme is in fact in a perpetual La Nina state. So the blue highlighted regions of this plot represent La Nina conditions, whereas the Chen 20% scheme shown on the far right has oscillations resembling the control more closely. And we also find that the Chen 5% scheme results in a shift in the ITCZ northward, whereas again the Chen 20% scheme results in oscillations more similarly to the control. So the next experiments I will describe are from my recent study that Doug mentioned, Emme et al. 2025 in GRL. So the first 4 experiments I'll introduce here are shorter 20-year sensitivity experiments testing the deployment of MCB in a single hemisphere and season at a time. So for 3 months of local summer and winter in either the northern or southern hemisphere. These seasons were chosen based on their likelihood to induce cooling. So summer is expected to induce more cooling as there is more incoming solar radiation to reflect, and winter less likely. So these single hemisphere deployment locations are shown in purple on the maps here, each covering 20% of the ocean surface, similar to the Chen 20% scheme. So we chose to base these locations off the Chen 20% scheme. As I mentioned, it was the most successful in climate restoration from that study. However, the Chen 20% scheme had really precise deployment locations following the gridbox to gridbox pattern of CESM2, which may be more difficult to implement in other models. So here instead we decided to contain MCB deployment to a single hemisphere at a time in more uniform mid-latitude regions in order to facilitate model intercomparison. Emme et al. 2025 showed that these summer deployments lead to more global cooling than the winter deployments, but the cooling pattern's non-uniform, largely cooling the seeded hemisphere. The winter MCB strategies result in a much less cooling overall, but the impact on temperature is more uniform. Additionally, we found that the single hemisphere summer MCB strategies trigger a larger shift in the ITCZ, so I highlighted that here with the boxed regions, whereas the winter deployments result in oscillations more similarly to the control. And finally, the single hemisphere summer MCB strategies trigger more frequent La Nina conditions, as it's not quite as clear as it was with the Chen 5% scheme with the Niño 3.4 index plots. I also calculated the percentage time spent in La Nina, so I show that in each of the plots here. For the time period of these simulations, which is 2035 to 2055, the control is in La Nina for 62% of the time. So each of these experiments do trigger more frequent La Nina conditions. However, the summer MCB strategies result in more frequent conditions, especially that southern hemisphere summer strategy at 80% of the time being spent in La Nina. Likely, we are seeing these large differences in climate outcomes by summer versus winter MCB due to the climatology of each of these seasons. The winter mid-latitudes are associated with fronts, cyclones, and storm tracks, which are able to distribute that cooling a bit more evenly across the globe, whereas these summer MCB strategies create a more regional cooling effect, largely contained to the deployment locations. So the next experiments were run for 35 years, deploying MCB for 6 months in the fall and winter in a single hemisphere at a time. And while these do produce more cooling than the winter-only strategies, they also result in negative climate outcomes, such as non-uniform cooling, and also a shifted ITCZ. So we finally combined those two single hemisphere fall plus winter strategies to deploy MCB year-round in the fall and winter months of either hemisphere. So this scheme leads to a much more uniform cooling pattern than the previous experiments, and also avoids shifting the ITCZ, likely because the forcing is more balanced by deploying MCB in both hemispheres throughout the year. Additionally, this scheme avoids triggering perpetual La Nina, with a similar result to the Chen 20% scheme. So now that we have a background in the global climate impacts of each of these MCB experiments, let's dive into the impacts on polar regions, specifically polar surface temperature, sea ice area, and sea ice thickness. We first analyzed the change in multi-year monthly mean surface temperature within the polar caps compared to the present day, or controlled 2020 to 2039 conditions. This target of the present day represents 1.5 degrees C warming above pre-industrial levels under SSP 24.5. So the horizontal line shown at 0 represents no change with respect to the present day. And the left plot here shows the 4 sensitivity experiments, as well as the controlled 2035 to 2055 average in black. And we find that this controlled climate change scenario projects that temperatures will increase throughout the year. And Arctic temperatures are reduced most here by Northern Hemisphere summer, with the other MCB strategies here resulting in a similar, with a similar result to the control, especially that Southern Hemisphere winter strategy shown in green, which largely follows the control throughout the year. Shifting to that right plot, temperatures are projected to increase more intensely later on in the century, especially in the winter months. And MCB reduces this most by the Chen 5% ensemble, Chen 20%, and Northern Hemisphere plus Southern Hemisphere fall plus winter strategies. The Southern Hemisphere fall plus winter strategy shown in blue here does improve Arctic temperatures relative to the control, but the temperatures are above the present day level throughout most of the year. Here I show the same thing as the last slide, but instead for the Antarctic. In the Antarctic, the control also shows temperatures will rise throughout the year, and again more intensely later on in the century. And for our sensitivity experiments, Southern Hemisphere summer is the only experiment to reduce Antarctic surface temperatures below the present day level. All other experiments follow the control and are even warmer than the control in some months. Shifting to that right plot, we also find that Antarctic temperatures are reduced most by Southern Hemisphere fall plus winter, Chen 20%, and Northern Hemisphere plus Southern Hemisphere fall plus winter. Overall, we find that the polar surface temperature decreases most when MCB is deployed in the same hemisphere as the ice, especially with summer deployments. Now shifting gears to the impacts on sea ice, I show here a similar plot to the temperature plots, but instead the change in multi-year monthly mean sea ice area with respect to the present day level. Unsurprisingly, we find the experiments most successful in reducing the Arctic monthly mean surface temperature are also most successful in restoring the monthly mean sea ice. That is for our sensitivity simulations, the Northern Hemisphere summer strategy, with the other strategies performing better than the control in most months, but not consistently restoring the present day level. And for our other experiments, we find the Chen 5% ensemble, Chen 20%, and Northern Hemisphere plus Southern Hemisphere fall plus winter strategies are able to restore that Arctic sea ice, with the exception of a few months, shown here. Additionally, the experiments most successful in reducing the Antarctic monthly mean surface temperature are also most successful in restoring the monthly mean sea ice. That is for our sensitivity experiments, the Southern Hemisphere summer strategy, with the other strategies here actually performing worse than the climate change scenario. And for our other experiments, Southern Hemisphere fall plus winter, Chen 20%, and Northern Hemisphere plus Southern Hemisphere fall plus winter are able to restore that Antarctic sea ice, with the Chen 20% scheme having a restoration of sea ice above the present day level throughout the entire year. Our other experiments shown here, the Chen 5% ensemble and Northern Hemisphere fall plus winter, perform similarly to the control, but in some months perform better than the control. Here I show a time series of the summer minimum sea ice area for the simulation periods of the MCB experiments, so on the left until 2055 and on the right until 2069. In the Arctic, as I mentioned previously, sea ice reaches a minimum in September, and in the Antarctic in February. The control here shows a decreasing trend in sea ice throughout the century, with sea ice nearly reaching zero by 2069. And in the Antarctic, the trend is a bit less clear, but we do see sea ice area below the present day level for about the last 2 decades of the simulation. An interesting result exemplified by this time series is that Northern Hemisphere's summer deployment of MCB improved sea ice in the Arctic, with sea ice area well over the present day level for several years, but in the Antarctic, it leads to decreased sea ice area relative to the climate change scenario. And obviously, doing climate intervention, we would want to at least perform the same as climate change or better. So this negative non-local impact is a major risk of climate intervention and highlights how critical it is to consider both local and non-local impacts from MCB strategies. I didn't expect to see this result necessarily. I thought it would just follow the control with the opposite hemisphere, but we hope that this can inform future studies in designing and analyzing their MCB deployment strategies. As MCB has largely been considered able to be deployed as a regional cooling strategy, as opposed to CSEi being considered a more global cooling strategy, we hope that this result highlights that these regional cooling impacts may still have remote consequences. Additionally, this time series highlights the Chen 5% ensemble is most effective at restoring the sea ice initially after MCB deployment, with sea ice area well over the present day level for several years, but there is a significant drop-off that occurs about midway through the simulation, and sea ice area is below the present day level for about the last 10 years of the simulation. Also notable about the Chen 5% ensemble, it's able to restore Arctic summer minimum sea ice, but not Antarctic, even though it does produce a significant amount of global cooling. As I mentioned previously, this cooling by the Chen 5% ensemble is largely non-uniform, and the cooling is largely confined to the low latitudes. While it still is able to restore Arctic sea ice, perhaps due to changes in ocean circulation, it's unable to really do much for the Antarctic. We find that there are few experiments able to restore the multi-year summer minimum mean sea ice area at each pole. I know there are a lot of numbers in this table here, but let's just focus on a few. So this top row here shows the present day level sea ice for the summer minimum, and each of the orange highlighted boxes is able to restore that present day level. So in the Arctic, only Northern Hemisphere summer is able to restore the present day level of summer minimum sea ice. And in the Antarctic, more strategies are successful, including Southern Hemisphere summer, Southern Hemisphere fall plus winter, Northern Hemisphere plus Southern Hemisphere fall plus winter, and Chen 20%. So we see here also that the summer minimum sea ice area in both poles are restored only when the MCB is deployed in the same hemisphere as the ice. So we also wanted to understand the spatial patterns of change in the sea ice by MCB. So here I show the Arctic and Antarctic summer minimum sea ice fraction difference from the present day for each of the sensitivity experiments first. In the Arctic, we unsurprisingly see a decrease in sea ice area by the control scenario, especially over the Canadian archipelago, and we also get decreases throughout the Arctic cap. But the opposite hemisphere or winter MCB strategies largely resemble that control, which is what we expected given the time series results also showed minimal sea ice restoration by these strategies. But the Northern Hemisphere summer deployment leads to a pretty significant recovery of Arctic sea ice here. We get an increase in sea ice at the Arctic cap and also alleviated decreasing sea ice fraction over the Canadian archipelago. In the Antarctic, the opposite hemisphere or winter MCB strategies also resemble the control, with Southern Hemisphere summer here showing the best restoration of sea ice. We see increases in sea ice fraction throughout the Antarctic. Sea ice fraction at both poles decreases more later on in the century, especially over that Canadian archipelago region I mentioned, and also within the Weddell Sea in the Antarctic. Each strategy in the top row improves Arctic sea ice, especially the Chen 5% ensemble and Chen 20%. In the Antarctic, the response to MCB is less consistent, but as I mentioned previously, there is low confidence in Antarctic sea ice projections, so it's important to keep this in mind when looking at the results. Notably here, the more balanced mid-latitude MCB schemes like Northern Hemisphere plus Southern Hemisphere fall plus winter and Chen 20% are able to restore the sea ice in both the Arctic and Antarctic, but the most susceptible approach, Chen 5% scheme, again, only improves Arctic conditions. It seems necessary to deploy MCB in the mid-latitudes of the Southern Hemisphere in order for Antarctic sea ice to be restored. And this will be demonstrated again with some of the following results. We also wanted to understand how our MCB experiments impact the thickness of sea ice. So here, just for the sake of time, I only show the experiments most successful in restoring the sea ice. And we find that the changes in summer minimum sea ice thickness spatially follow the changes in sea ice fraction. Like for sea ice fraction, we get a decrease in sea ice thickness over that Canadian archipelago, as well as throughout the Arctic cap. And our MCB schemes are able to alleviate that decreasing sea ice thickness, especially with Northern Hemisphere summer. We get slight increases in the sea ice thickness at the Arctic cap there. And in the Antarctic, again, the impacts of MCB are a bit less consistent strategy to strategy, but we do see improvement here from each of the strategies shown. While this is not included in my preprint paper, I did want to show some of the impacts of how MCB impacts the winter maximum sea ice. So the Arctic reaches a maximum in March and in the Antarctic in September. So here I show a similar time series to one of the previous slides for the summer minimum, but again for the month of winter maximum at both poles. We see a different trend for some of the MCB experiments in restoring the winter maximum as opposed to the summer minimum mean sea ice area. Of the sensitivity experiments, of course, we see Northern Hemisphere summer restoring sea ice to the present day level throughout the simulation, of course with some oscillations due to the variability of sea ice. But we also see here the Northern Hemisphere winter and Southern Hemisphere summer deployments are able to improve the winter maximum sea ice area much better than they did for the summer minimum. In the Antarctic, however, only Southern Hemisphere summer is able to restore the winter maximum sea ice, like for the summer minimum. And shifting to the Arctic again for our other experiments, the Chen 5% ensemble is able to restore the winter maximum sea ice throughout the entire simulation above the present day level, as opposed to the summer minimum where we saw that drop off about midway through the simulation. And Southern Hemisphere fall plus winter here largely follows the control for about the first half of the simulation, but it starts to increase and actually surpasses the present day level for about the last 10 years. In the Antarctic, though, again, only the experiments able to restore the summer minimum restored the winter maximum. The multi-year average winter maximum sea ice area is also better restored by the MCB experiments than the summer minimum, especially for the Arctic. So if you refer to the table here, calculations are the same as the last table, but instead for the month of winter maximum. We find in the Arctic, multiple experiments are able to restore the present day level, not only Northern Hemisphere summer. And in the Antarctic, the same experiments are able to restore the winter maximum as the summer minimum. So we see here that the Arctic winter maximum sea ice area is able to be restored by opposite hemisphere or winter deployments, in contrast to that summer minimum. But again, in the Arctic, only the experiments deploying MCB within the southern hemisphere mid-latitudes are able to do anything for the Antarctic sea ice. And this just highlights some of those schemes. Now the plot here shows the winter maximum sea ice fraction difference from the present day in the Arctic and Antarctic. The experiments shown here are again just the most successful for the sake of time. And we find that MCB restores winter maximum sea ice area in different regions than it did for the summer minimum. Largely, it appears to change sea ice at the sea ice edge. We see a decrease in sea ice fraction from the control throughout most of the Arctic. We do see this increase within the Labrador Sea, but it has been shown previously that CESM2 leads to a freezing of the Labrador Sea. So while this might not be a physically realistic result, it has been shown that this is just a bug in CESM2. For the MCB experiments in the Arctic, MCB restores sea ice at the sea ice edge, especially by the Chen 5% ensemble and Chen 20%. For the MCB experiments in the Antarctic, we're also able to restore sea ice at the sea ice edge, especially by the Chen 20% scheme here. Interestingly, Northern Hemisphere summer and Southern Hemisphere summer deployments are able to restore the winter maximum sea ice, even though they deploy MCB within the summer months, suggesting a possible change in the larger scale dynamics that would lead to impacts later on in the year. We also saw this with the fall plus winter strategies, restoring the summer minimum sea ice area. And while it isn't exactly clear what dynamical changes are occurring here just from the results I show, it would be really interesting to investigate this in the future so that we can better understand how MCB impacts the climate system. The change in sea ice thickness also spatially differs from the changes in sea ice fraction for the month of winter maximum sea ice. The control plot here shows an Arctic-wide decrease in sea ice thickness, and this is largely recovered by these MCB deployments, especially Northern Hemisphere summer. We get an increase in sea ice thickness throughout much of the Arctic. And in the Antarctic, we get a decrease in sea ice thickness again throughout the entire region, which MCB is largely able to recover, especially by that Chen 20% scheme. It is important to note the sources of uncertainty in our study with regard to the CESM2 CAM6 configuration. First, CAM6 winter sea ice thickness is biased thin over the historical time period, which leads to lower Arctic September sea ice area compared to CESM2 WACM6, which is their whole atmosphere configuration and observations. So this biases future projections of summer sea ice conditions. We may be showing a lower estimate of Arctic sea ice with the experiments shown here. Additionally, the aerosol activation scheme in CAM6 leads to low drop number concentrations, which induces a positive shortwave cloud forcing bias in the mid-latitudes. So this may exaggerate the efficacy of mid-latitude MCB as simulated by CESM. And there is uncertainty in and a lack of representation of secondary ice processes in Earth system models, which complicates the simulation of mixed phase clouds and cloud forcing. So there is just uncertainty in general within these secondary ice processes, so it's not clear how improving that representation may impact the MCB experiments shown here. But all of this, sorry, did you have, oh, I thought you were raising your hand. But all of this work, all of these uncertainties are the work of model development currently. I know there is a configuration of CESM2 CAM6 which tunes the sea ice conditions to better match observations. So we didn't use that just because these schemes were originally focused on temperature restoration, and we were just utilizing model output that was already available. But I would suggest if you are interested in this kind of work, looking into that configuration. Additionally, the aerosol activation scheme is currently being worked on at NCAR, so hopefully we'll see improvements to that very soon. In conclusion, the deployment location and seasonality of MCB are critical considerations for restoring polar sea ice and also achieving stable climate outcomes at the same time. We found that the balanced mid-latitude deployments, Chen 20% and Northern Hemisphere plus Southern Hemisphere fall plus winter, improve polar conditions in both hemispheres while also avoiding those negative climate outcomes of triggering perpetual La Nina and shifting the ITCZ. And while the tropical deployment Chen 5% only improves Arctic conditions, it also leads to those negative climate outcomes of shifting the ITCZ and perpetual La Nina. Additionally, deploying MCB in the same hemisphere as the targeted sea ice is most effective for restoration, especially with deployment in these summer months. But it's important to keep in mind that there are likely trade-offs associated with any strategy you're looking at. For example, we saw Northern Hemisphere summer improves Arctic sea ice, but leads to decreased Antarctic sea ice relative to climate change. Future work, we'd like to run longer simulations of those sensitivity experiments. Again, they were 20-year experiments, but running it for a longer period of time may tell us whether or not there's a drop-off like we saw with that Chen 5% scheme. Additionally, to assess the robustness of these results, it would be really helpful to run multiple ensemble members and also perform a multi-model comparison just to see whether or not these results are consistent across different configurations. The largest uncertainty currently in simulating MCB are the aerosol cloud interactions within Earth system models. As I mentioned, we're just modifying the cloud drop number concentration here instead of actually injecting the sea salt aerosols, which of course has limitations associated with it. So in the future, we will be directly injecting the sea salt aerosol for MCB in the model once that aerosol activation scheme is improved. In my postdoc, I'll be looking at polar MCB still through the lens of Arctic MCB, so super excited to be starting that work soon. And for the last chapter of my dissertation, I'll be looking at the atmospheric chemistry impacts of MCB, which I also find very interesting, so if anyone wants to chat about any of these things, I'm more than happy to. But with that, I'll thank you all for your time and attention, and take any questions you may have.
Wow, thank you, Erin. Questions from the audience? I will ask a question. Oh, go ahead.
Why? I don't know if this is the standard, but why do you use like the least susceptible 20% and the most susceptible 5%? Like, how do you choose that percentage?
So I wasn't the one who did that study. They tested a couple of different percentages though. So they did the 5% because that was kind of what has been done in MCB previously, and they just really wanted to highlight some of the negative climate outcomes associated with that. But I think they tested a range of about 10 to, I want to say 40 or 50% for the least susceptible. So I did show, I can go back even, I did show the results of those other schemes. It's just that the Chen 20% scheme was the best at restoring climate to the climate target. So they tested four total least susceptible ones, but the Chen 20% hit the climate target. The ones that are 30% and 40% overshoot and do too much cooling. So that's why we chose to look at the 20% one.
I'm going to ask a question. Actually, it's more of a speculation. I noticed that the fall and winter simulations, where you actually deploy the cooling fall and winter, seem to do better than just the summers alone. And I would like to suggest that that's because of a lifeboat effect. And the idea is that when you're deploying cloud brightening in the summer, you're actually trying to save ice that's going to die anyway.
Okay, yeah.
That's going to melt. But it's the fall when the ice that's just barely made it through the summer needs to survive in order to make multi-year sea ice. That's the best time to go in there and nudge it into a place where it can survive. And then also the winter deployment then again is allowing you to make more sea ice, but there you're probably relying on atmospheric heat transport because you're not actually affecting the sunlight coming in, but you're more affecting sunlight elsewhere that is then either being transported or not transported as we need there. So I call it the lifeboat effect.
That makes sense. Yeah,
Okay.
I would say that makes sense.
Well, thank you. Other questions? There's one in the way back, and then we'll come up here.
Sorry, I'll
Way
try.
back first.
Yeah, sorry, I'll try to project. Maybe I just missed it, but what was the seasonal timeline for the Chen 20% and Chen 5%? As in, when were these deployments occurring?
So the deployments vary on a monthly basis, but they are deployed year-round. So the deployment maps are shown here for each month. They deploy it over the same percentage area of the ocean in each month. Just the location differs month to month.
Please.
I wanted to piggyback off of your question. If you're interested in doing more of the deployment in the winter or fall months, then you're also taking advantage of the increased cloud cover because there's more cloud cover during those months.
Good point.
Right, yeah. And like I said, like with those storm tracks, you're probably able to distribute that cooling a bit more evenly rather than just kind of sitting on top of that one location cooling with the summer.
So are you taking into account those more positive feedback loops into the consideration when you're doing your planning for deployment then?
Well, so we didn't look, sorry, can you repeat your question?
In terms of those types of positive feedback loops, those and other forms of the same type of feedback loops, are you considering those when you're making your deployment plans?
Yeah, I think that's why we were targeting the winter, the winter seasons, I guess. Yeah.
David.
So this is a bit off the main topic. It's a terrifically clear talk. Thank you very much. And this is a question about how you, as a kind of young researcher working on MCB, think about technical feasibility. And I'm not trying to target you individually. I think I just worry the MCB field is kind of ignoring the fact that maybe we don't know how to do it.
Yeah, I mean, that's a fair point. I've been asked.
Yeah, do you think about, like just to give you, like the best recent sprayer is 10 to the 12 particles per second, and you need something like 10 to the 16 or 17. And so I'm inclined to say that unlike sulfuric acid charges, which we know how to do, we simply don't know how to do this. And there's no, so I guess I'd like to just have you speculate. I know it's not your expertise, but how do you think about it? How do you think about whether you and other people should talk about it?
Yeah, I think that it definitely could be thought about a bit more, at least from the modeling community. I personally don't really think about it too much. Like I've been asked, like, well, how many ships would it take to deploy this? I don't know. But, it's definitely something that I think should be taken into consideration. But I do think that it is good to have a multitude of strategies that are being researched rather than just focusing maybe only on CSEi, just to see, in the future, like God forbid, we do have to consider these deployments. We have research done on a multitude of strategies that could potentially work. Maybe we show here MCB doesn't work, but that's something good to know as well.
I agree agree, but this won't show if it doesn't work technically.
Right.
I think the issue is, so of course I agree that we should look at lots of different things, but at what point do we kind of cut it off and say we actually just don't know how to do this?
Yeah.
Just to challenge you, like, you could look at adding sulfur back into shipping. It
Yeah.
could kill more people.
Yeah.
It's a thing we know we could do.
Yeah, I think it's a fair
Somehow
point.
We're looking at 2025, 2035, 9 years from now, for a technology we can't even do at the lab scale level. I think at some point it's just not real.
Yeah, I think it's a fair point. I know there are labs that do focus on, those types of things and are trying to develop those sorts of technologies. That's not my expertise, so I don't, think about it too much, but I think it's definitely something the MCB community should keep in mind and continuously talk about throughout, the coming years where we do get a little bit deeper into this research.
I'll stop intervening now, but I think my 2 bits would be people in your situation or new to this should at least start their talk saying, hey, this is assuming this can be done.
Mm-hmm.
Because there's a lot of great SRM technologies
Yes.
that in principle would be great, but are just not possible.
Mm-hmm.
Say something about it, don't leave it hanging.
Yeah.
I'm going to ask the last question, and it might be both towards David and Erin, and that is, what I take from Erin's talk is that there's a variety of effects that come from deciding what time of year, what locations that deployments are being done. Does that kind of variety and complexity also exist for stratospheric aerosol deployment? Meaning, are there talks that would be similar to what Erin has given us today? Wonderful talk, by the way, Erin. That would apply to stratospheric aerosols.
I mean, maybe you have a better answer for that. I know I've seen multiple different papers look at, different latitudes of deployment. I'm not sure if I've seen seasonal deployments, but again, I mostly look at MCB, so I'm not, as up to date on the CSEi literature maybe, but maybe you can answer that better.
There might be commonalities too,
Yeah.
between the two, so much could potentially be learned from that.
Yeah.
So I think this variety of complexity that you're probing is still very important, regardless of whether we have the technology today
Yeah.
to span things. But with that, what I would like to do is thank Erin one more time. And anyone who has further questions, just come up and talk to us.